So, next is about the Lenz law. So, what this Lenz law states means it is useful in giving the direction of induced current or the polarities of induced EMF. In order to get the directions of induced currents or the polarities of induced EMF, we can go with the Lenz law. So, what the Lenz law says? It is very simple. The direction of induced current or the induced EMF polarities will be in such a way to oppose the cause producing the effect. So, the direction of induced current or the polarities of induced EMF will be generated in such a way to oppose the cause producing the effect. To oppose the cause producing the effect means we know that just like we being the children sometimes always will oppose whom? The cause for us. Who is the cause for us? Our parents will be the cause for us. So, if our parents says at this age of 18 years or 17 years, in the teenage always will oppose our parents who are the cause for us. If they asked us to study, we won't study. If they ask us not to study, we will study. So, always our mentality will be not matching with the parents' mentality. Yes or no? So, we are opposing the cause for us. In the similar way here also, it says that, Lenz says that the direction of induced EMF or the direction of induced current is always in such a way to oppose the cause producing the effect. So, here if you see, this is a coil. For our better understanding, I am taking a loop or a coil, okay, and here I will be choosing a bar magnet. This is a bar magnet, this being the north pole and this being the south pole. Now, this north pole is brought closer to the coil. This is a coil like this, coil is like this, and this is a bar magnet, and this is north pole. North pole is brought closer. When the north pole is coming closer, flux linked with the coil is increasing or decreasing. When the bar magnet is away, less flux is there. When it is coming closer, more flux is linking with this coil. So, flux linked with this is increasing. Flux linked with this is increasing. I will indicate the flux like this. When it is coming closer, the flux linked with this coil is increasing. So, when there is an increase in the flux, which is responsible for the induced current, then the direction of induced current should be in such a way to decrease the increasing flux. Decrease the increasing flux. So, when it is brought closer, flux is increasing. Therefore, induced current should be in such a way to oppose the increasing flux. That means it should decrease the increasing flux. Then what is the direction of induced current? The direction of induced current will be like this. The direction of induced current will be in this way. Then what is this? This will behave like what? This will behave like a north pole. Or what is the direction of induced current? Anti-clockwise sense. So, when the induced current is anti-clockwise like this, the flux will be, developed induced flux will be opposite to the increasing flux. So, according to Lenz law, increasing flux should be decreased and decreasing flux should be increased. In this case, when the bar magnet is brought closer to the coil with the north pole coming towards the coil, then induced current will be anti-clockwise. Second diagram I will take. Let me choose, this is the coil, and the same bar magnet I will be choosing. This is north pole and this is south pole. In this case, this bar magnet is moved away. When the bar magnet is moved away, flux linked with this coil is decreasing or increasing. Here it is increasing and here it is bar magnet is moving away, flux should decrease. When flux is decreasing, according to Lenz law, the direction of induced current should be in such a way to increase the decreasing flux. Increase ಆಗ್ತಾ ಇದ್ರೆ decrease ಮಾಡಬೇಕು, decrease ಆಗ್ತಾ ಇದ್ರೆ increase ಮಾಡಬೇಕು. So, then what should be the direction of induced current? The direction of induced current in this case will be like this, clockwise. Clockwise like this. Then I can represent with the south pole like this. The tips of this letter will indicate the direction of current flow. Now, one more thing logically which you can remember, I will tell you. Without any confusion, we can draw the directions for induced current. What is that means? You know the simple logic that like poles will repel each other and unlike poles will attract each other. What is the simple logic that we know? Like poles will repel each other and unlike poles will attract each other. Now, when north pole is brought closer, it should be repelled. North pole is repelled by which pole? Again another north pole. Yes or no? So here if you see north pole is moving away, going away it should be attracted according to Lenz. Therefore, going away it should be attracted means north pole should be attracted means which pole should be developed? South pole should be developed. So this is how we can simply find the direction for induced current without having any idea about the what actually happens here. So actually what is happening means when the bar magnet is brought closer, flux linked with the coil is increasing, therefore direction of induced current or induced EMF is in such a way to oppose the increasing flux. That's why the direction of induced current will be like this. Or simply thinking, when north pole is coming closer, it should be repelled. Coming closer, it should be repelled. Going away, it should be attracted. Yes or no? So converse effect should be there always. North pole coming closer, it should be repelled, then north pole should be developed. North pole means anti-clockwise direction. Now, north pole is moving away, it should be attracted. That means north is attracted by which pole? South pole. South pole means which kind of current? Clockwise current. Is it clear? So this is how we can get the direction of induced current or induced EMF, polarity of induced EMF by using the Lenz law. Is it clear? So in previous year examination, many times they asked what is the significance of Lenz law. So the significance of Lenz law is what means? The significance of Lenz law is to get the direction of induced current or the polarity of induced EMF. What is the significance of Lenz law? The significance of Lenz law is to get the direction of induced current or the polarity of induced EMF. And this Lenz law is based on a particular principle called conservation of energy. Lenz law is based on which conservation principle? Conservation of energy principle. But most of the materials will give answers like this. What is the significance of Lenz law means? Many of the materials they have given that significance of Lenz law is conservation of energy. It is wrong. Please be noted. So the direction, what is the significance of Lenz law? Significance of Lenz law is to get the direction of induced current or the polarity of induced EMF, and it works on the principle of conservation of energy. Is it clear? Now I will tell you a few more examples so that we can easily get the directions for Lenz directions for induced current or induced EMF. Look here, I will be taking this is a coil, and here there is a south pole and this is north pole. When south pole is brought closer, what is the direction of induced current? It's very simple. When this is the south pole coming closer, it should be repelled. South is repelled by whom? Another south pole. Therefore here what should be the pole? South pole should be there. So at the tips if you keep the arrow, it is nothing but clockwise. So direction of induced current is clockwise in this case. And next example, if this is south and this is north and this is going like this. Now in this case, what is the direction of induced current? Now here this is south and this is north. South is moving away. When it is going away, it should be attracted. Attracted means south is attracted by which pole? North pole. So just draw north and keep arrows at the tip. So what is the direction you are getting? Anti-clockwise. Is it clear or not? In this way, we can get the directions for induced current simply using the Lenz law. And as I told you that it is based on the conservation of energy principle, if it does not obey conservation of energy principle, let us see what is going to happen. So in this case, if I am bringing the bar magnet closer, north pole is formed. Therefore, if I want to move still inward, then I need to do work against the magnetic force of repulsion. In this case, north pole is going away, south pole is developed, and that is attracting. So if I want to move it like this, I need to do work against the attractive force. Here I need to do the work against the repulsive force, north and north are repelling, and here I need to do the work against the force of attraction. Here also south and south will repel. Therefore, to move the magnet closer, I need to do work against the force of repulsion, and here I need to do the work against the force of attraction. In all these cases, what you understood means, in order to move the magnet, so I need to do work against either the force of attraction or the force of repulsion. Yes or no? But now, all these things are in accordance with the conservation of energy principle. Suppose if I have, instead of north pole, or here, let me take this example, instead of south pole, here a north pole is developed. Here a north pole is developed. Then what is going to happen? Here north pole developed means induced current is like this. That is anti-clockwise in sense. Now, if I release a bar magnet here, north will repel this north. Therefore, without the actual moment of the magnet by me, the magnet will move on its own because of this repulsive force. So, the magnetic field will do the work and on its own it will go like this. And here also, if this is south pole, then if a bar magnet is released here, it will be coming closer on its own. So, no one has to do the work, yes or no, which is against to that. That means, if you release it here on its own only, it is going to move, which is against to the conservation of energy principle. Is it clear or no? So, if here a north is replaced with south, that is violating the conservation of principle, and here also it is violating the conservation principle. Therefore, according to Lenz, the direction of induced current or the direction of induced polarity is always in such a way to oppose the cause producing the effects. Okay. And here you are telling that we are doing work against the forces I am telling. Then where does that work gone? That work done is dissipated in the form of energy. That work done by us will be dissipated in the form of what? Energy. Is it clear? This is about the Lenz law. And next we will be discussing about the motional EMF. Next is about the motional EMF. Motional EMF, the name itself says that EMF that is developed because of the motion of the conducting rod. So let me choose a uniform kind of magnetic field here. Here magnetic field is uniform, which is not varying, and that magnetic field is directed into the board. Into mark says that the physical quantity is going into the board. Here this physical quantity representing into is nothing but the magnetic field. Therefore, I can say that there is a uniform magnetic field B bar which is directed into the board here. And in this one, I will take a rectangular shaped metallic wire. Conducting metallic wire will be taken like this, and here I will be taken a rod like this, name it as some PQ, and this is R and this is S. Now PQRS represents a metallic wire, and in this one if you see, if this metallic wire PQ is moved in this direction, and this PQ wire can be made to move on the rails SP and RQ freely, and there is no friction here. So we need to neglect the friction topic here, or that is the frictional effects will be neglected here. So the rod length PQ is nothing but the length of SR, which is equal to L, and let me choose this is equal to some X. This is the initial situation. So in order to study the motional EMF, I am considering a uniform magnetic field which is directed into the board, and on the plane of the board I am taking a rectangular shaped wire PQRS, and in this one the rod PQ can be moved freely over the rails SP and RQ, and here there won't be any frictional effects. Now the length of PQ is nothing but length of SR, which is equal to L, and the length of RQ is taken as X. When this rod is moved in this direction with the speed of V, then what is happening? The rod is coming like this, means then flux linked with this loop is changing or not changing? Flux linked with this loop is getting changed. How the flux linked with this loop is changing? Already we studied that flux phi is equal to what? We know that flux phi is equal to B bar dot A bar, and which can also be written as flux is equal to B into A into cos theta. Here B stands for magnetic field, A stands for area vector, and theta is the angle between B bar and A bar. If you consider this area, for this area vector will be outward like this, and magnetic field is directed into the board. So what is the angle between B bar and A bar? Angle between those two will be 180 degrees, because area vector is a vector which is perpendicular to the given surface area and directed outward, and magnetic field is directed into. So this can be written as BA cos 180 degrees, that is equal to BA cos 180 is minus 1, which is equal to minus BA. This is the negative flux. So the magnetic flux may be positive, may be negative, may be 0 also. So whether it is electric flux or magnetic flux, flux may be positive, may be negative, may be 0 also. Negative flux says what and positive flux says what? Negative flux says that the lines are coming into, and Positive flux says that the lines are moving away. Is it clear? Incoming flux is taken as negative and outgoing flux is taken as positive. Now here, when this rod is moved like this with velocity v, in a small interval of time delta t, this rod will, PQ will be displaced from here to here. The rod is displaced by small amount from this location to this location, and this speed is v only. In a small interval of time delta t, this was happened, and in that small interval it has covered a linear distance is equal to say some delta x. Okay. Now what is the area covered in that small interval? Area covered is nothing but this length L into area of this part, which is nothing but length L into delta x. That is a small elemental area covered. Is it clear? So what is the small flux that is changed? Therefore, delta phi is equal to change in flux during interval delta t. Change in flux means magnetic flux during small interval delta t. During small interval delta t is nothing but delta phi. Delta stands for small. That is equal to minus delta of B into A. Here we know that B is a fixed quantity as it is uniform. I can write B outside, therefore minus B into delta A. What is this delta A? That is minus B into delta into length into x. That is equal to minus B into L being constant, I am writing it outside. So this is delta phi. Is it clear? Okay. Now, according to Faraday's laws of induction, which law of induction? Second law of induction. According to Faraday's second law of induction, Faraday's second law, what I will be having? The amount of induced EMF E is equal to minus of delta phi by delta t. Yes or no? The negative rate of change of magnetic flux is nothing but EMF, induced EMF. So this implies E is equal to minus of delta phi is nothing but B into L into delta x divided by delta t. So this is by using equation 1. Using equation 1. What is this? This implies E is equal to minus B into L into, what is delta x by delta t? Delta x by delta t is nothing but velocity v, since v is equal to delta x by delta t. Yes or no? Therefore, finally what you got? E is equal to minus BLV we got. Okay. So when the rod is moved in this direction, what is the direction of current we are getting? Direction of current is like this. Direction of current will be like this. That means the current is flowing in which direction? So when it is going like this, flux through this is increasing or decreasing? When this is going like this, area covered is increasing. Area increases, flux increases. So flux increases means induced current should be in such a way to oppose the increasing flux. Inward flux is increasing. Inward flux is increasing. Therefore, that increasing flux should be decreased. Therefore, according to Lenz law, the induced magnetic field should be outward. So therefore, the direction of induced current is anti-clockwise like this. Is it clear? This is how we can find out the direction of induced current. And the most important thing that I want to specify here is, now onwards, you should not treat this rod as a rod. You treat the rod as a battery, whose EMF is equal to BLV. BLV. So when a rod is cutting the magnetic flux while it is moving, an induced EMF will be developed across the ends of the rod. That induced EMF is nothing but BLV. Therefore, the equivalent circuit for this is like this. Suppose PQ rod is having some resistance of R, and this PS, SR and RQ does not have any resistance, then I can simply take like this. Here there is a rod is now replaced with a battery whose EMF is how much? BLV. Now onwards, the moving rods are not taken as the rods, but you assume it to be a battery whose EMF is given by E is equal to BLV in terms of magnitude. Then current is going like this. Let R be the resistance of this rod. Is that clear? So this motional EMF will be seen in which cases? When an aeroplane is moving, then across the two wings of the aeroplane, an induced EMF will be developed, and this induced EMF may be some undesirable or not requirable EMF. So because of that induced EMF, there is a chance for the plane to catch the fight. So that is to be nullified. Not only that, when a train is moving on the railway track, because of between the two wheels there will be an axle which is made up of conducting rod. When a train is running on the track, it is cutting the vertical magnetic field of the earth. So this is the train. If you assume vertical magnetic field of earth will be like this, while horizontal magnetic field will be like this. When the axis of the wheel is cutting like this, so then an induced EMF is developed across the two ends of the wheel, and this induced EMF will be used for glowing some of the bulbs in the trains. Is it clear? When a train is running with some speed v, then axle connecting the two wheels is also running with the same speed, and that axle is cutting the vertical component of magnetic field of earth. Because of that, an induced EMF is developed, and that induced EMF is given by BLV. In this case, sometimes they will ask how much EMF will be developed. Suppose earth magnetic field, if I take it as vertical component of earth magnetic field, if I choose as say some 5 into 10 to the power of minus 5 Tesla, let me choose. And length of the axle, you take it as some 1.5 meter. Length of axle means the two wheels of the or railway track length. So perpendicular separation between the two rails, you take it as 1.5 meter. And if the train runs with the speed of 54 kilometer per hour, 54 kilometer per hour, what is the induced EMF between the two ends or between the axle is the question. Then E is equal to 5 into 10 to the power of minus 5. Length is 1.5. V is equal to 54 kmph means 54 into 1 kilometer per hour means 5 by 18 meter per second. In first year we studied that 1 kmph is equal to 5 by 18 meter per second. 18 goes in 54, 3 times 3 5s are 15. 15 meter per second. Now substitute it here, then what you are getting? 15. So this is nothing but 15 15s to 25 will be known for us. Therefore I can write it as 5 into 22.5 into 10 to the power of minus 5. Now its value is 5 into 5 25, 5 2 will be there, and 2 now again 12, 1 2 2 5. So here this point will be there here, then this is into 10 to the power of minus 5 volt. Or else this will be equal to how much? That will be equal to E is equal to 0.1225 into 10 to the power of minus, or I can write it like this, 1.225 into 10 to the power of minus 3 volt, or else 1.2 millivolt approximately. This much voltage is developed. So when the speed of the train increases, the amount of voltage also increases, because I can't change the length of the axle and I can't change the vertical magnetic field. So being BV and L fixed, if the speed of the train changes, induced EMF also changes. Okay, this induced EMFs will be useful for glowing some small electric bulbs. Is it clear? So this is about the motional EMF. So guaranteed question will be asked in the competitive part of examination, and that too a problem will be related with the train or aeroplane. So when the plane is moving horizontally, then it is cutting the vertical magnetic field of earth. Then between the two wings of the plane, an induced EMF will be developed, which is an undesirable value, and that is to be nullified. So this is about the motional EMF. Is it clear? So once look here, this is not 1225, it is 1125. Therefore this will be 1.125. So approximately 1.1 millivolt. Calculation mistake happened here, please correct it. Okay, so once look here, we have calculated the motional EMF. Now we are going to find out the induced current, induced charge, and the power required in moving the rod. These things will be going to discuss here. Now in order to discuss that, first let me treat this circuit as a simplified circuit. Now I can treat the rod to be what? A battery, whose EMF is equal to how much? BLV in terms of magnitude. Therefore I will simply take the as I have chosen PQ rod of length is having the resistance while the remaining part is not having any kind of resistance, let me take the resistance of that PQ rod is equal to R. Then the entire resistance of this PQRS loop will be R. Now this is small r, and now here you have to assume there is a battery like this, whose EMF is equal to how much? BLV. Now it is in current electricity we have seen that when a resistance is connected to a battery, then a current is there in the battery, in the circuit. Let me take that current is equal to I. I is the current. According to Ohm's law, I can say that, according to Ohm's law, what I can say, V is equal to IR. Here V is nothing but EMF, therefore E is equal to I into small r. This implies E by R is equal to, otherwise I is equal to, current in the circuit is nothing but E by small r. This implies current I is equal to, E stands for BLV divided by R. BLV divided by R, where R is the resistance. This is the formula for induced current. Is it clear? Then if I want the induced charge, what I need to do? Induced charge is nothing but, we know that current I is equal to Q by T. Current I is equal to Q by T. Therefore Q by T is equal to BLV divided by R. This implies Q is equal to BLV divided by R into T. This is nothing but the induced charge. Induced charge in this case. Okay. And now, if the rod is moved like this, when you are moving the rod like this, is there any force acting on this rod? So when the rod is moving like this, current is induced in this one. And now it is a current carrying rod. This is a current carrying rod which is present in the magnetic field. When the current carrying rod is present in the magnetic field and it is moved like this, because of this one, there is a magnetic force acting on this rod. What is the magnetic force formula? F is equal to Bill sin theta. Here, current is like this and magnetic field is like this. So, angle between the length vector and the magnetic field vector will be 90 degrees. Therefore, force is equal to BIL. So, magnetic force acting on the rod. Magnetic force acting on moving rod. Acting on moving rod. How much is the force here? F is equal to BIL. That is nothing but B into I means what here? I is nothing but BLV divided by small r into L. So that is equal to B square into L square, B square L square V divided by R. This is the formula for magnetic force. What is the direction of this magnetic force? When the current is passing like this, magnetic field like this, what is the direction of magnetic force? Magnetic force is acting like this. And you are moving the rod like this. So magnetic force is trying to pull the rod like this and you are moving the magnet like this. That means in order to move the magnet in this direction with constant speed V, you need to do some work against the magnetic force. And that work will be dissipated in the form of energy. Then how much work is to be done? So here when the rod is moved like this, the work done in moving the charges from here to here is nothing but work done in moving the charges over a length of L. Work done in moving the charges over a length of L is given by which one? Work done in moving the charges. Work done W is equal to force into displacement, that is equal to force is B square L square V divided by R into displacement is over the length of L. So then I can take it, or if I move the rod like this in this direction by x distance, then I can take it as into x. Is it clear? This work done will be dissipated in the form of energy, and power required is nothing but power required or power dissipated. Power dissipated, power is equal to, we know, force into velocity, that is nothing but B square, force is B square L square V divided by R into V. So finally power dissipated is B square L square V square divided by R. This is the amount of power that is dissipated when the rod is moved like this with velocity V against the gravitational force. In order to move the in order to move the rod like this with the constant speed v, then magnetic force is coming into play, which is trying to bring the rod backward, or restoring force, I can say. To do work against that force, I need to do some work, and some power is dissipated, and the power required or dissipated is nothing but b square L square v square divided by r. Is it clear? And one more thing is, induced according to Faraday's laws of induction, EMF is equal to minus d phi by dt, minus d phi by dt, and this E can be written as I into R is equal to minus delta phi by delta t. From this, induced current I is equal to minus 1 by R into delta phi by delta t, and lastly current can be written as delta q by delta t, that is equal to minus 1 by R into delta phi by delta t. This implies delta q is equal to, this delta t will go off, minus delta phi divided by R. So if you observe here, induced current depends upon time, induced EMF depends upon time, but induced charge is independent of time parameter. Is it clear? Induced current is depending upon time, induced EMF is also depending on time, but induced charge is independent of the time parameter. Is it clear? This is about the motional EMF. So next is rotational EMF. This concept is especially useful for your competitive part of examination, varying from CET to JEE exams. For all kind of competitive examination, this formula will be useful, rotational EMF formula. The EMF that is generated because of the rotation of the rod in the magnetic field is nothing but rotational EMF. Motional EMF means when the rod is moving, when a conducting rod is moving in the magnetic field, then you will be getting the motional EMF. And now here, when a conducting rod is rotated in the uniform magnetic field, then we will be having an EMF that is called as rotational EMF. Let me choose, there is a uniform magnetic field here. There is a uniform magnetic field here which is directed into the board. A uniform magnetic field is taken and which is directed into the board. Now in this magnetic field, I want to rotate a conducting rod in anti-clockwise sense. Let me choose, this is a conducting rod. This is a conducting rod whose length is equal to L, or whose length is equal to R. Now fixing one point, let us consider this point A is fixed and this is B. Now fixing the point A, if this rod is moved like this in anti-clockwise direction with angular speed omega, then what is going to happen? When the rod is moving like this, is it cutting the magnetic field or not? Magnetic field is like this, directed into, it is cutting the magnetic field. So therefore, in a small interval of time delta t, the B will come from here to here, yes or no? So this is the new position of the rod after some time. This is the new position of the rod after some time. In that small interval of time, it has described an arc here. So, and a small angle is also described here, that is delta theta, let me choose, in a time interval of delta t. Now, how much induced EMF is developed? From the basic idea, that is from Faraday's second law, what I can say? From Faraday's second law, induced EMF is nothing but what? E is equal to minus d phi by dt. But here phi is nothing but B into A. Here angle between B and A is how much? B and A is 180 degrees. B is into the board, area vector is outward, therefore 180 degrees. Therefore I can take it as cos 180. Since phi is equal to BA cos theta is the formula. So that is cos 180 is how much? Minus 1. Minus of minus is what? Plus. Therefore, d by dt of BA. As you know that B is a magnetic field which is uniform, that means it is a constant. You can take the constant out of differentiation. Therefore, B into dA by dt I can write. But what is this A? A is nothing but the area described by the rod. It is nothing but the sector area. Sector area means how much? The sector area is nothing but half into base. You can assume it to be a triangle. Then I can take it as area of that is d by dt of area of sector, that is area of triangle, half into base into height. This is base length, nothing but arc length, half into arc length into height. Height is nothing but length of the rod, which is taken as r into r. So what is arc length? Arc length is nothing but r into delta theta. According to mathematics we studied, arc length is nothing but r theta. Therefore I can write it as E is equal to B into half comes out d by dt of arc length is nothing but r into delta theta into r. So here half into B into this r is a fixed quantity. The length of the rod does not changes when it is rotating. Therefore r is constant, r into r square, you can write it outside, d by dt of theta. So what is this d by dt of theta? It is nothing but angular velocity. Rate of change of angular displacement is nothing but angular velocity. Therefore I can write it as half into br square into omega, since angular velocity omega is equal to d theta by dt, which we studied in first year. So finally this is a formula for rotational EMF. When a rod of length r rotates in a uniform magnetic field with angular speed omega, then amount of rotational EMF developed between the ends of rod is nothing but half br square omega. Is it clear? Half br square omega is the formula for calculating the rotational EMF. Good morning students. In the previous class we have studied about the introduction of electromagnetic induction, and there we discussed about the Faraday's laws of induction and then Lenz law and motional EMF concepts we have discussed. Yes or no? And today's class we are going to discuss about the eddy currents and induction phenomenon. In this induction phenomenon we are discussing about the self induction as well as the mutual induction phenomenons, and finally we are going to learn about the AC generator. These are the topics that are remained in this electromagnetic induction chapter. Coming to the previous topics, what are Faraday's laws of induction? So already I told you that Faraday's first law says that whenever there is a change in magnetic flux linked with the coil, then there is an induced EMF, and if it is a closed circuit along with the induced EMF, then there will be also an induced current. So what is responsible for the induced EMF or the induced current? It is a change in magnetic flux linked with the coil, but not the relative motion between the coil and the magnet. So the important thing that we have noticed in the Faraday's first law of induction is the change in magnetic flux linked with the coil is responsible for the induced EMF or the induced current, but not the relative motion. Is it clear? And second thing is Faraday's second law of induction. First law says that induced EMF is there, and second law says that how much induced EMF is there. The amount of induced EMF is equal to what? The negative rate of change of magnetic flux linked with the coil. Second law will give out the amount of induced EMF, and according to that law we are saying that the amount of induced EMF E is equal to negative rate of change of magnetic flux linked with the coil. So this is Faraday's second law of induction, and most of the problems will be related with this formula only in this chapter. And now this negative sign is in accordance with the Lenz law. What is Lenz law means? The Lenz law is used for finding out the polarity of the induced EMF. That means the significance of Lenz law is to identify the polarity of induced EMF or the direction of induced current. And this law states that the direction of induced EMF or the induced current is in such a way to oppose the cause producing the effect. And this Lenz law is based on the conservation of energy principle. Yes or no? And then we studied about the motional EMF as well as the rotational EMF cases we have discussed. And according to motional EMF, when a conductor is moving in a magnetic field, then the amount of induced EMF is equal to BLV. And based on this, we will be having the problems, especially for 2 marks as well as for the 5 mark level problems. And this is the motional EMF formula. When a rod of length L moves in a magnetic field D with velocity V perpendicularly, then the induced EMF is given by E is equal to BLV. And later we studied about the rotational EMF. When a rod is rotated in a uniform magnetic field
with constant angular velocity omega, then the rotational EMF is given by the formula half BL square omega, where L is the length of the rod and omega is the angular speed. If a rod of length L is rotated in a uniform magnetic field with a constant angular velocity omega, then the rotational EMF is given by the formula half BL square omega, which will be useful for the competitive part of examination. And now in today's class we are going to study about the eddy currents. What are eddy currents? These eddy currents are also called as Foucault currents. Foucault currents. Why? Because these currents were discovered by the scientist named Foucault. Hence the name eddy currents or the Foucault currents. Why the currents are called as eddy currents? What are meant by eddies? Eddies are nothing but just like the whirlpools that are seen in the natural phenomenon. Whirlpools means if you see whenever water is flowing, suddenly at some places we will be seeing the whirlpools. Whirlpools means the circulatory motion of the water. So those things are said to be the whirlpools or eddies. And how these currents are developed is the question. And in the previous chapter we have studied that whenever there is a current carrying coil, when current is passing through the coil, this coil will produce a magnetic field and the coil is behaving like a magnetic shell. Yes or no? When a current of 5 amperes passes through the coil and in this direction you will be having the magnetic field. So a current carrying coil is responsible for producing the magnetic field. Now, and there is a particular path is there in this case. What happens if instead of a coil, if I take a bulk sheet of metal and that bulk sheet of metal is kept inside the magnetic field, what is going to happen? What is going to happen when a bulk sheet of metal is kept in the varying kind of magnetic field? When a bulk sheet like this is kept in a varying kind of magnetic field, or whenever the magnetic flux linked with this plate or sheet is changed, then there will be some currents that are induced, and those currents will be circulating type of currents, and those circulating currents are looking like the eddies or the whirlpools. Hence the name eddy currents or the Foucault currents or whirlpool amount of currents I can say. Whenever a metallic sheet is or a metallic plate is oscillated in a varying kind of magnetic field, then induced currents will be developed, and these induced currents will be looking like eddies or the whirlpools, hence the name eddy currents, or as the currents are noticed by the scientist named Foucault, these currents are also called as Foucault currents or the eddy currents. And here because of these eddy currents, there will be some advantages as well as some disadvantages are also there because of the eddy currents. What are the advantages and what are the disadvantages we are going to discuss here. Coming to the disadvantages, because of these eddy currents, there will be some energy losses in the transformer. So in the transformer, there will be a core material, and that core is made up of some metals or magnetic materials. When eddy currents are developed in this core material, then there will be an energy loss because in the form of heat, and that energy loss is due to the eddy currents. Due to eddy currents, the efficiency of the transformer is going to be decreased. So the efficiency of the transformer can be decreased because of the eddy currents that are developed in the transformer core materials, which are made up of metallic sheets in some cases. And because of these eddy currents, what is happening means there will be some damping will be there, electromagnetic damping will be there. So that I will tell you here. Suppose this is a metallic sheet. Let me choose this is a metallic sheet. And this metallic sheet or the metallic plate, a bulk material, when it is made to oscillate in the uniform kind of magnetic field like this, it is if there is no magnetic field here and this is tied to a insulated thread and it is made to oscillate like this, you can see the oscillations like this. Just like in the case of a simple pendulum, we can notice the oscillations in this fashion. Yes or no? Suppose if I keep the magnetic field which is directed from one side to the other side, then what is going to happen we will see. So let me choose the case. Let me choose the case here. This is a north pole of the magnet and this is a south pole of the magnet. When this is north pole and this is south pole, from north to the south there will be a magnetic field directed from north pole to the south pole. So let me choose that these here two magnetic poles are there, this representing the north pole and this representing the south pole. In between these two poles, if I make a metallic sheet or plate to oscillate, what is going to happen? I will see. So here physically assume that there is a north pole here and there is a south pole here. Okay. Now I will say when a magnetic field applied means you have to assume that the two poles are there. Magnetic field not there means the two poles are not present. So assume that two poles are present. If I say switched on, if I say switched off, magnetic field is absent. Is it clear or not? So if I say magnetic field is switched on, what is happening? There is a north pole and south pole. Just assume. So if I say that switched off, then assume that there are no two magnetic poles. Now switched off case. Switched off case, you can see the oscillations like this. The oscillations of the metallic sheet can be noticed in this way. Now switched on, immediately the metallic plate is going to rest position. Is it clear or not? So switched off, again it will continue to oscillate. Switched on, it is the oscillations are damped immediately. Why this damping is happening is the question here. So if I say switched off, it is oscillating freely. Switched on, it is coming to rest instantly or immediately it is coming to rest. Why this metallic plate is coming to rest is the question here. Why this metallic plate is coming to rest means it is oscillated in the magnetic field. When it is oscillated in the magnetic field, the magnetic flux linked with this metallic plate is going to change, and this changing magnetic field is responsible for the induced currents. And those induced currents, if you see, they are just like the eddies in the water. Hence the name, hence the currents are called as eddy currents or the Foucault currents. Is it clear or not? Diagrammatically, I will show the representation of oscillations of this or the direction of induced currents in the metallic sheet. So let us consider the case here pictorially, where a metallic sheet or a bulk sheet of or a plate is made to oscillate in the uniform kind of magnetic field. Let me choose. This is the one of the magnetic pole. So let me choose here. This is representing the south pole of the magnet. This is representing the south pole of magnet like this. Let me choose. This is representing the south pole, and here there is a north pole. There is a north pole here. I am representing the north pole here. This is the north pole. Now between the north pole and south pole there will be a magnetic field, and that is directed from north to south. Therefore I will indicate it like this. This is the uniform kind of magnetic field developed between north to south. And here I will take a pivot, and from that pivot I am releasing a metallic plate. This is a metallic plate. This is a metallic plate which I am releasing. Now, when this metallic plate comes like this and then coming like this, it is oscillating in between the pole pieces of the magnet. When it comes like this, what is going to happen? When it comes into the magnetic field, flux linked with this plate is increasing. So flux is increasing. In what direction? Flux is moving from here to here. When this plate comes like this, magnetic field in this direction is increasing. So when the flux is increasing, according to Lenz law, the direction of induced current must be in such a way to decrease the increasing flux. Flux is increasing in this direction, it should be decreased, means the induced flux should be from there to this. That means the induced current should be directed in this way. So when the induced currents are like this, then magnetic flux developed will be in this way. Therefore, the direction of induced current will be in this way. So when it enters into the magnetic field, there will be an induced current developed in this direction. Now when this comes out of this, when this is coming out of this, or I will draw a little bit clearly like this. So this is the pivot here, and when it comes out, then what is going to happen? Here when it is coming out, the flux linked with this is decreasing. Therefore, the induced flux should be enhance the already existing flux. Therefore, the direction should be in which direction? It should be in this way. So, when currents are like this, when currents are induced in this way, so it should already existing flux is in this direction, but that is decreasing. According to Lenz law, when the flux is decreasing, inducer flux should increase the decreasing flux. Therefore, inducer flux should be in this way, means the current should be in which direction? Clockwise sense in this way. Is it clear? So, here in this case, when it is entering, flux is increasing. Therefore, inducer current should be in such a way to decrease the increasing flux. Where it is coming out, the flux is decreasing. Therefore, inducer current should be in such a way to increase the decreasing flux. Therefore, the direction of inducer current will be like this. So, when it is entering, it is in one direction. When it is leaving, the inducer current is in opposite direction. Because of these circulating inducer currents developed in the metallic sheet, what is happening? Eddy currents are developed. So, here in the previous case, when there is a coil and the flux linked with the coil is getting changed, then there is a inducer current in a particular fashion. But here there will be a circulating kind of or whirlpool kind of currents will be developed in the metallic sheet. Here it is a bulk sheet or a bulk plate I can consider. Now, I will consider the second situation where the effective area of the plate is going to be reduced. How I can reduce the effective area of the plate means, suppose if this is the plate, this is a plate which is oscillating like this. I will cut the plate like this. So, I will make the gaps for the plate. In this way, I will make the gap. Then what is going to happen here? So, in such a case, when I cut it like this, so when I cut it like this with gaps, the effective area is going to be decreased. So, in this case, the effective area is reduced. Same thing here also I need to draw. So, in this case what happened? The amount of area is reduced. When the area reduces, then the amount of induced current is also noticed to be reduced. After cutting the plate, when it is kept in the magnetic field, when it is not in the magnetic field, it will oscillate easily or it will oscillate without any damping. When the magnetic field is switched on, then it will oscillate slowly like this. So, oscillatory speed is reduced, but still it is oscillating. So, though there is a damping, but the damping is less when the effective area is reduced. Why the damping is less means the inducer current amount is reduced. So, inducer current is depending upon what here? It is depending upon the effective area. It is depending upon what? It is depending upon the effective area. By reducing the effective area, we can reduce the eddy current values. That is why when you want to increase the efficiency of the transformer, whenever there is an eddy current loss, then what you need to do is the core material is to be laminated. Laminated means the given metal plate is divided into a number of sheets, and those sheets will be laminated together with each other with the help of some insulating material. Okay, using an insulating material, again they will be grouped up. It is just like the case of, suppose if I take this as a whole, if you can see it as a plate, but this plate is consisting of number of sheets. These are the number of sheets. So, these sheets can be laminated by using a gum. I can paste them and you can have a laminated kind of metal. Is it clear? So, if it is treated as a metal, then this metal can be made up of number of sheets like this. These are the number of sheets, and these sheets will be laminated with the help of a material called insulating material we are using for that purpose. Is it clear or not? So, that is how we can laminate. By laminating, what happens means the eddy currents will be reduced. When eddy currents reduces, then the heat loss will be reduced. When the heat loss reduces, then the efficiency of transformer can be increased. This is how eddy currents will be affecting the efficiency of the transformer. So, what are eddy currents? They will be asking in the board examination. Eddy currents or focal currents are nothing but the induced circulating currents. They are the induced circulating currents that are developed in the bulk sheets or bulk plates whenever the magnetic flux linked with the plate or sheet is going to be changing. So whenever the magnetic flux linked with the metallic plate or sheets varies, then there will be an eddy currents, or then there will be an induced circulating currents will be developed. Those induced circulating currents are called as eddy currents or the Foucault currents. And because of this one, what happens? You have seen the damping of the oscillations when the metallic sheet is oscillated in the uniform kind of magnetic field. Is it clear or not? When it is oscillating in uniform kind of magnetic field, when it is entering and leaving, the flux is changing. When it is entering, flux is increasing. When it is leaving, flux is decreasing. And whenever there is a change in flux, there is an induced circulating currents called as eddy currents. And what are the advantages of these eddy currents? Nowadays, we are having the modern day type of electric trains are there. In these kind of electric trains, we can use the eddy currents for the braking system. In the modern day trains, we can use the eddy currents for the braking system of the trains, electric trains. How they can be used means, just above the rails, the electromagnets will be arranged. So whenever the train is required to be stopped, then what they will be doing means, just the electromagnets will be switched on. When the electromagnets are switched on across the rails, then induced currents will be developed. Because of this induced currents, damping will come into play. Due to the damping, the train will come to rest. So instantly, without any energy loss. So here it is a smooth braking system, I can say. So this type of braking system is called as smooth braking system. So in the braking system of the trains, nowadays we are using the eddy currents. How they are using the eddy currents means, just above the rails there will be electromagnets, and these electromagnets are used to produce the magnetic field. If I want to stop the train, then simply the electromagnets are switched on, then magnetic field will be developed across the rails. Because of the magnetic field linked with the rails, then induced currents will be developed called as eddy currents, and because of these eddy currents, damping will come into play, and therefore the rail will come to rest immediately. And this is a smooth kind of braking system. Is it clear or not? So this is how we can use the eddy currents as modern day braking system in modern braking system of trains. We can use the eddy currents. Secondly, these can be used as the electromagnetic damping cases. In electromagnetic damping, what is this electromagnetic damping means? In certain kind of galvanometers, there will be a non-magnetic type of metallic core will be there. In certain kind of galvanometers, there will be what kind of core material will be there means, non-magnetic metallic cores will be there. So whenever current passes through that coils, and when the coil is oscillating in the magnetic field, what happens? Immediately induced currents called as eddy currents will be developed just like this, and immediately the galvanometer will come to rest. So the immediate resting of galvanometer can be seen due to the eddy currents developed in the coils. Just like a copper coil, if I consider, in a moving coil galvanometer there will be a coil made up of copper. Whenever current is passing through that coil and it is oscillated in the magnetic field, damping will coming into play, and that is called as electromagnetic damping. In this way, we can use the eddy currents for the electromagnetic damping of the galvanometer. So third one is, we can use the eddy currents in the induction furnaces. In induction furnace, we can use the eddy currents. So how this can be used as the induction furnace means, whenever the currents are passed through the metallic sheets, and those currents will produce the heating effect we discussed, and the amount of heat produced is given by I square RT. According to Joule's law, in current electricity we have studied that the amount of heat produced is proportional to what? Square of the current. So when the eddy currents are more in amount, then what happens? The amount of heat produced is also more. If this heat is sufficient to melt a metal which is kept in that which is oscillated, then what happens? The metal is going to be melted. So in induction furnaces, we can use the eddy currents. When eddy currents are developed in the metallic sheet which is to be melted, then if that heat produced is equivalent to the heat of melting of the metal, then that metal is going to be melted. So in the formation of alloys, alloy is nothing but a combination of 2 or 3 metals. So first what we have to do, those given metals are to be melted, and those molten form of metals will be remixed to form an alloy. In this way, we are using the eddy currents in the induction furnaces for melting of the metals. So these are, and lastly, we will be knowing or we will be familiar with the one of the important application of eddy currents. That means in olden days in our childhood, we have seen the electric meters at our homes. In those electric meters, there will be a black color box, and in that box there will be one shiny metallic disc will be there. If this is the electric meter, main meter, if you go for that electric meter in olden days or in our childhood, if you see, these kind of electric meters are available. There will be one metallic disc will be there with a shiny silvery arrangement will be there, or silver coating will be there for that metallic disc. So when the current is used in our home, or when you are consuming the electric power, how much electric power can be consumed is measured in terms of electrical units. How that electrical units will be noted means, if this metallic disc completes one circular motion, then 1 unit is consumed. Like that, there is a calibration. So if you see that electric meter, there will be a black color box will be there, and in that black color box there will be a circular metal plate will be there, coated with a part of it is coated with a silver, and now our silver kind of shiny arrangement will be there. So when current is consumed, then this induced currents or the eddy currents are developed. Because of that eddy currents, this metallic circular metal plate is revolving. When it is revolving like this, when it is rotating. When it is rotating like this, you can see the strip coming and then going, again it is coming. So this is used in the electric meters, analog type of electric meters. Nowadays we are not using the analog type of electric meters, but some 5-6 years before we are using that analog type of electric meters. Even in villages nowadays we are using these kind of electric meters, but now we are in a electronic type of meters we are using, or digital meters we are using for getting the how much electrical power consumed by us in our houses or in any industry. So olden days they are using these kind of analog type of electric meters, where there will be a metal which is rotating, and that rotatory motion is because of the eddy currents that are developed. Is it clear or not? So this is about the applications of eddy currents. So 4 important applications we have discussed here. In the modern braking system of electric trains, we are using the eddy currents. For electromagnetic damping or in deadbeat galvanometers, we are using the eddy currents, and we are using the eddy currents in the induction furnaces to melt the metals. To melt the metals, we are using these induction furnaces where we are using the eddy currents, and we know the idea that the amount of heat produced is directly proportional to the square of the current. Here I stands for the eddy current. And now the last thing is, in the electric meters, we are analog type of electric meters, we are using the eddy currents. These are the applications of eddy currents. What are eddy currents? Whenever the magnetic flux linked with the metallic sheet changes, or linked with the metallic plate changes, then there will be a circulating type of induced currents. These circulating induced currents so developed are called as eddy currents, and these are noticed by the scientist named Foucault. Hence we can also call them as Foucault currents. Understood these things? So how we are going to decrease the eddy currents means by reducing the effective area. When the effective area reduces, induced current is also going to be reduced. In this, is it clear or not? In this way, we can study about the eddy currents, and next we are going to discuss about the induction. How many types of inductions are there? We are going to discuss.